The background picture that I'm showing today is a picture taken from the back of the uh, uh, the spacecraft that was launched yesterday by Virgin Galactica, with lots of innovation involved in it. Instead of sending a rocket into space, they carried the spaceship on a simple airplane. So it opens up the new way for commercial uh, commercial aircraft, passenger aircraft, rather than the military aircraft only applications of somehow NASA and Elon Musk approach. The important aspect of it is that, look here, this is the thickness of our atmosphere here. A very thin layer, like the crust of the surface of an apple, that all life on Earth, including ourselves as humans, are living in. And we are stewards of that life on Earth. We are not supposed to go and destroy it. We are supposed to protect it. You heard about this summer, dozens, literally dozens of people dying in Canada. In Canada, which is supposed to be a colder climate than, say, the United States, just from the effect of heating. So this is a hurdle for humanity that we have to pass, and we can control it by uh, developing energy sources as renewables and nuclear energy. So this is basically what the spacecraft shows up. I'm going to turn my face, and you can see here, this is a real picture. That's the back of the Unity 22 spacecraft, showing the Earth's atmosphere under it. Uh, you are invited to open up uh, their video and watch it. And you're also invited to even participate in a sweepstake, where you can get 2 seats on one of the future flights of passengers into to the edge of space. Okay, that will get us to emphasize in our class this semester the aerospace aspects, because the next steps would be maybe a base on the moon, and then humanity will find its way to the asteroid belt and to Mars. And a trip to Mars, as we'll see later, requires practically a nuclear engine because of its higher specific impulse than a chemical engine. I'll make clear why is that so as we proceed further. As we do this today, we are going to look at the other concepts of fission systems that have been advanced. Some of them are still on the drawing board, and some of them are really taking shape. One aspect of no development is the possibility, actually it is a reality right now, floating nuclear barges. And that, so I'll start with this one. And this has been developed for remote locations, maybe in the Arctic region, or for the desert areas. And that happened just 2 years ago. And you could see here a floating nuclear barge. It's was developed by the Russians academic Lomonosov. And the barge basically is a nuclear power plant based on technology that was developed for icebreakers. And definitely it is using a nuclear reactor. You could see a very modern control room here. And this is a picture of the interior of the floating barge, where you have the nuclear reactor in the center and the turbine hall, all of them on board the barge that can be moved from one place to the other. This was a pioneering floating nuclear power station. It would sail 5,000 kilometers or 3,000 miles from Murmansk to the far east of the Russian, basically of Russia. And The United States Army, in fact, pioneered that idea in the period of 1968 to 1976. And it used a floating nuclear power plant at the Panama Canal for canal operations. They called it the MH-1A Sturgis. It was a converted World War II cargo ship, but it was later decommissioned. The academic Lomonosov uses two KLT-40S reactors derived from a time-tested design used for Russia's nuclear-propelled icebreakers. For icebreakers, ultimate engine definitely is a nuclear reactor for the huge amount of power it can provide and the need that of not getting refueled with diesel fuel every once in a while. It can go on for a year or a year and a half without refueling. These reactors have a low power output. They generate each only 35 megawatt thermal power. And notice here I'm specifying it is not electrical, it is not rated power without the TH or the E. It is only thermal power that is turned into shaft or screw power to propel the ship into ice and open up channels for other cargo ship to proceed in general. That is not just a matter of icebreakers providing channels for naval navigation, but also it can provide power for a whole city of 100,000 residents. They are already working on the second floating nuclear power station. It will use a different type of a reactor. They call it the RITM 2000M. It would require more space and it will require more, it will generate more power and require more space. So you could see here, there is some advancement in the nuclear field. Another interesting advancement is what is called the autonomous battery reactors. What is autonomous in that? What is autonomous in it is that imitation of the reactors that are used for naval propulsion, for nuclear submarines. These reactors do not get refueled every year or a year and a half. They are designed with a very high enrichment of the uranium to last as a load of fuel the whole lifetime of the reactors. So in that case, the idea is being applied for small units of reactors that would be sent to the field, used, and then at the end of their using the fuel loading, returned back and dismantled and recycled, literally in that case. So there is a trend of building small reactors also for remote locations in general. The General Electric pioneered that with the Hitachi from Japan, and they proposed a small prism reactor, which we have shown in one of the previous chapters. Bill Gates have been suggesting that the nuclear industry is not innovating, so he started his own company. It's named Terra Power, and in the state of Washington. And he's also developing some new concepts in nuclear energy. One of the people there introduced himself to me at the conference, and he is one of the electrical engineers who took our course right here. So that is very rewarding. So let us talk about reactors that are self-contained, or in that case, battery reactor. Obviously, in that case, you need to have a large amount of initially loaded as fuel into it as uranium-235. So they use high enrichment of the fuel, and we'll have a whole chapter on the enrichment of the fuel to understand what it how it happens. And it is also have to do the breeding that we mentioned last time. So if it's a uranium-based fuel, you produce plutonium, but then you burn it as it is produced in the core and produce more power. One interesting application is a city in Alaska called the Galena. And that is a city that is very far north, and electrical power is necessary for the survival of that city. Their winter temperatures can dip to minus 60 degrees Fahrenheit or minus 51 degrees Celsius, and daylight is scarce because of the short days during the winter. Now, that town is paying 28 cents per kilowatt hour for its electricity. If you look at your electricity bill here, you pay probably 6 cents per kilowatt hour. So it's a very expensive electricity. It is 3 to 4 times the average, the national average. It is, it has it has a population of 700 people on the Yukon River, 275 miles west of Fairbanks, Alaska, and 550 miles northwest of Anchorage. So you could see it's a very, very far north location. The Japanese company Toshiba has been trying to help them. So they came up with a design of what they call the 4S reactor. That stands for super safe, small, and simple 4S reactor. And in that case, it is offering them, in fact, a free reactor just for testing the concept and maybe making it available to other people. Now, it is a fast reactor using sodium as a coolant so that you breed plutonium and then burn it in the reactor itself over its own lifetime. And it's a very low pressure reactor. It uses sodium, so that's a safety feature in that type of a design. Notice here that now they have a reactor that is very tall in the structure, and they have it even underground as another safety feature. And it's an integral type of reactor, like the prism reactor that the General Electric company has shown before. So the reactor is underground now. The reactor itself, the reactor core, as well as a heat exchanger that generates steam for a steam generator and a turbine producing the electricity. With sodium, as you know, sodium is a liquid metal, so it conducts electricity. So in that case, they are using what they call an electromagnetic pump right here. The electromagnetic pump uses a perpendicular electric and magnetic field. And in that case, you get the Joule force, and in that it's a V cross B. We'll cover that as we go along later in the course. And to propel or to move the sodium coolant from the reactor core to the heat exchanger. So an electromagnetic pump, interestingly enough, does not use any moving parts. It's just two perpendicular electric and magnetic fields. Another use of the electromagnetic pump is to pump liquid metals in foundries when you want to move, say, iron without moving it on an impeller that the molten iron can melt. The reactor tries to conserve the number of neutrons that are used in the fission process. So they have a core that rises up and then is brought in back down into the core itself. It has a simple one single control rod there in the center. The number of neutrons is conserved by not allowing those neutrons to leak from the system. So the whole inner core is raised out in between an area that is called the reflector. So that would be an annular region that has a good reflector for neutrons. That would be a low Z element like graphite maybe. And if you want to increase the power, you control it with a control rod, but the reactor would shut itself out if you withdraw the core out from the reflector region at the bottom. The tech specs or the technical specification is that this is a system that produces 30 megawatt thermal of power, And if you take an overall thermal efficiency in the conversion to electricity as 1/3, then the electrical power output would be 10 megawatt electric. Compare this to existing large utility level nuclear power plants. These produce something in the range of 1,000 megawatt electric. So it's really 1/100 the power output or the capacity of large power plants. So there is most probably a market for this for small locations, remote locations, and small cities that cannot afford to buy the 100 megawatt electric or the 1,000 megawatt electric nuclear power plant. The interesting aspect, and that's why it's called a battery reactor, is that the core lifetime is fully 30 years. So you send the reactor to the site, it operates for 30 years. After 30 years, you withdraw it. Now, notice that in that case, that core cannot be accessed in terms of the produced plutonium in the fuel. So it is extremely proliferation resistant. So nobody can access that plutonium in the core. It goes back to the manufacturer, the core is dismantled, the plutonium is separated from the uranium-235, and a new reactor would be sent to the site after 30 years. Because it would be a fast reactor, fast meaning that the neutrons used in the fission process are not moderated. Well, it's used sodium as a coolant. Remember, you'll find that in that case, those fast neutrons allow a better breeding because they produce more neutrons per fission than in uranium-238 than they produce at thermal energies when they are moderated. It uses a fuel that is metallic uranium mixed. It's not uranium dioxide like in existing light water reactors, the pressurized water reactor and the boiling water reactor, but it's a mixed oxide. So it's a metallic uranium, and not mixed oxide anymore, metallic uranium and 24% and 24% plutonium. And the cladding is then is zirconium in that case, 10%. The primary electromagnetic pump, there are two pumps just for reliability, and if one needs maintenance, then you have, the other one is available in that case. It is not a very large reactor. You could see that the tube lengths of the intermediate heat exchange is no more than 2.6 meters in general. And the steam generator type is a 1-through double wall tube helical coil. Why double wall? Because we worry about the interaction of sodium with water. The same as lithium interacting with water, producing a hydroxide, then releasing hydrogen, and the hydrogen now becomes very explosive. That is one of the hazards or the risks from using lithium-ion batteries in the Tesla cars in general. And because Alaska is very active in terms of seismicity, earthquakes, it has basically an isolation system that will protect the reactor. So this is the leading concept in terms of, and in fact, there is a pilot plant that Toshiba is experimenting with. Here it is. You could see that is a parallel configuration. It's not the integral design that I have shown earlier, but it's a similar design where you have a separate reactor vessel here with the core of the reactor, and then you have a heat exchanger. But the heat exchanger again has, again, that electromagnetic pump, EMP. And they have a primary one and a secondary one for the case of an accident. And that would be SG for the steam generator. So this could be part of our future for spreading nuclear energy to remote locations of the world. That can be implemented more like for producing fresh water in arid regions of the world, on seashores, provide fresh water for agriculture and small cities, and providing both agro and industrial type of complexes for an increased world population. The same idea was applied by a group of national laboratories in the United States. They all combined together, or the Lawrence Livermore National Laboratory, the Los Alamos National Laboratory, Argonne National Laboratory, they tried to design something similar to Toshiba. And now they also use the acronym Small Seal Transportable Autonomous Reactor. Again, the other terminology for that type of reactor is a battery reactor. So let us see, they show us a picture of it right here. It would be 3 meters in diameter, very small. And in height, it would be 15 meters. And the standard man in drafting is shown here. It gives you an idea about the size. This is something that can be transportable on by trucks and or by a barge on a river. And you could see that's again an integral type of reactor. It's adopting some ideas from naval reactor technologies. You have the reactor core at the bottom and the steam generator together in the same large pressure vessel enclosure. So you minimize the possibility, like on land-based reactors, where a pipe breaks, say, through an earthquake, and you could lose the coolant in that case. Again, they use the new technology of an electromagnetic pump that doesn't have any moving parts. If you watched by any chance the movie Red October, you hear in the movie about the possibility of a propulsion system for that Red October submarine that is used, is called the, basically it uses an electromagnetic pump. It is named in the movie the Caterpillar Drive. The Caterpillar Drive would be an engine that takes, either provides the water surrounding the submarine with an electromotive force through the E cross B. E is the electric field, B the magnetic field force, or it can use a jet system. The jet would accelerate water going through the submarine itself and eject it from the back, almost like a rocket. It's a jet engine, in fact. So that was the concept in the movie, The Red October, of the Caterpillar Drive, a very advanced type of a propulsion system for nuclear submarines. The two, one aspect, of course, comes from one design, as I've shown you, comes from the Toshiba company. This is a design that we have seen from the an alliance of the national laboratories in the United States, but private business came in also, and a company called the Hyperion Power Module. So they're trying to take the commercialized small nuclear reactor modules along the same line as the ideas of the Los Alamos National Laboratories, and they build up a small reactor, and shown here in that diagram. It would be a single 25 megawatt electric unit. So thermal power, if it's 1/3 efficiency, would be 75 megawatt thermal. Again, let's make a distinction here. As good engineers of the future, megawatt thermal is not the same as megawatt electric. When you multiply the megawatt thermal, a common error in our first test, by the way, by the thermal efficiency, you get the megawatt electric. They're showing us a reactor system with 2 units, each one of them 25 megawatt electric, that utilities would have lots of, they can borrow money to buy it, or they may have their own funds to buy it. The 2 units are placed underground, as you could see here, for extra safety. And in that case, the reactor power is 70 megawatt thermal. The efficiency is about 1/3, so that's 25 megawatt electric. The lifetime is 8 to 10 years. So you replace it after the unit after 10 years. The structural material is stainless steel. The coolant now is not sodium. The coolant is not sodium. It's an alloy of lead bismuth, a lead bismuth alloy. That was pioneered by the Russians in their alpha class of submarines, a titanium hull submarine that could dive real deep. And because it has the power from a nuclear reactor, it could go real fast too, and use lead bismuth as a coolant You cannot call it a moderator because lead and bismuth have high Z materials, so they do not moderate the neutrons. So it was a fast reactor, fast in the sense that the neutrons used in it were fast reactors. The fuel enrichment was less than 20% uranium-235. Now, nuclear submarines go, in fact, to the 93% enrichment, but there is a rule by because they are thinking about export by the International Atomic Agency, according to the NPT, or the Non-Proliferation Treaty. Nations who signed it commit themselves not to use fuel that has an enrichment of higher than 20%. So they are designing it to conform to the IAEA guidelines. And in that case, it is not an optimal design, obviously. If they go to higher enrichment, like in nuclear submarines, they can have maybe a 30-year lifetime with an enrichment of 90%. But they're really trying to target markets all over the world where 20% cannot, uranium-235 cannot be recycled into weapons in general. So this is commercial. They're trying to, of course, get it licensed for use in the United States. Not to be outdone, the Europeans came up also with a similar idea. Urenco is the company in Europe that carries out the enrichment of the fuel. And we are going to cover a full chapter on the enrichment. This is a UK-based company. It is the second largest enrichment nuclear fuel establishment, basically with AMEC Foster Wheeler PLC, a generation, they're developing a generation of small modular reactors called the U batteries. So they call it the U battery. So they're using the word battery because you use the reactor at the site to produce electricity over a 10-year period or over a 30-year period, and then take the whole pressure vessel and recycle it after the 20-year period. So there is no access to the bread fuel that could be used into weapons. So the fear here is obviously proliferation and the use of the produced plutonium for weapons. They have it as they are not having really very advanced technologies there. So there's a reactor core here in a pressure vessel and a separate heat exchanger. So there is competition in building small units. This is how they conceptualize. First, look at the size of it. This is a standard man that is used in the drafting technology. And basically, they would have all the units of the reactor placed underground. You would have a reactor core surrounded by a heat exchanger, all of them underground. And after you use it, you remove, for the 10 years, say, you remove the lid and you take the whole thing, put it on a barge or on a truck, take it to where you would recycle the whole thing. Another important aspect of it is a company that has advanced more than all the others. That's NuScale. NuScale has one of our students too, who took from here, Illinois, as a vice president. I think he is Bob Knudsen, and he took our safety course, which will be taught the next semester. So our engineers here, our graduates and our alumni, your good friends, are really designing the first generation of nuclear reactors. It has undergone already, that system is very far advanced, a review by the Nuclear Regulatory Commission, the NRC, in 2017. So if you have, if you are running a utility and you want to buy it, it is available to you for purchase. What they do here is that they address one of the main issues that were noticed in the three major accidents that happened in the nuclear industry, which were the 3 Mile Island accident, the Chernobyl accident, and the Fukushima accident. The three accidents led to the melting of the cores of the reactors because even after you shut down the fission reaction in a nuclear reactor by inserting the control rods, the fission products continue generating heat for a period of time from 24 hours to 48 hours. If you do not provide cooling, in that case, that heat is enough to melt the core. This is called the adiabatic heating extent in nuclear reactors. That's unlike, of course, any other heat engine, where if you shut the fuel input, the reaction fully stops. In nuclear reactors, that heat continues being generated, about 6 to 8% of the thermal power, and you have to deal with it if you don't want to have a serious accident. One method of dealing with it is what we covered in the generation 4 reactors, the molten salt reactor, progressing from using solid fuel, where those fission products would be present, into a liquid fuel. And in that case, if you use a liquid fuel, you can separate the fission products and you don't worry about the decay heat. Their way of dealing with the decay heat is placing the reactor vessel itself inside a large container or containment structure containing water. The system is designed in such a way that the water doesn't need pumping, that it uses natural convection. It would heat the core, cool the core from the outside, and simply circulate within, they call it this, the decay heat, of course. And within a day, you'll find that excess supply of water around the core, without the intervention of any operator or human intervention, would cool the core. And it would cool the core for fully 30 days to get to the half the level of the coolant water surrounding a steel vessel. That's an integral type of a design, obviously, that would have the core at the bottom and the heat exchanger at the top. And it can even remain larger than 30 days if all the water is boiled off from the decay heat. Air around the pressure vessel would still cool it, but then the decay heat would be very, very minimal, and there is no problem with it. So that system is being licensed in the United States, and it may be the first small reactor really to come into use in general. This is another way to display how small those units are. This is a typical pressurized water reactor, of course, would be 1,000 megawatt. And basically, this is the NuScale's integral power reactor as well as steam generator. It's only almost the size only of one single steam generator in a typical utility scale power plant in general. So the application of small reactors came in after the 1980s financial crisis, where capital on a big scale was destroyed. Utilities, even though they need sources of electricity, they cannot get bank financing in the range of $4 billion or $9 billion. If you buy plant from South Korea, you can buy it for $4 billion for 1,000 megawatt unit. But in the United States, because of the regulatory levels that are some kind of excessive, it's $8 billion in general. The world population has a real energy problem. During the last 25 years, electricity supplies have been extended to 1.3 out of 7 billion people living on our Earth here. Yet still 1.6 billion people, or 25% of the global population, still have absolutely no access to electricity. 2.4 billion people rely on traditional biomass, burning wood, agricultural residues, and even animal dung for cooking and heating. And 99% of the population without electricity lives in the developing nations. So those small unit reactors can be a way of fighting poverty and improving the standard of living all over the world. According to the United Nations, about 13% of the world population does not have access even to enough food and water to live a healthy and productive life. Yet the ability, technology, and resources needed to produce enough food for every man, woman, and child in the world, they do already exist. And we don't have just nuclear energy. at our disposal, but we also have the renewables to seek. I'll stop sharing for any questions and go to the next chapter. So I'll open here the chat room for any questions. All right, since we are in a crash course over the summer, we do not waste time. We go and cover more of the concepts of nuclear reactors that are on the drawing boards. And we covered already the barge concept and the battery concept reactors, the autonomous reactors. Let's go to the idea that Bill Gates have been pursuing initially. The idea is what was called at some point the traveling wave reactor. So what is a traveling wave reactor? The traveling wave reactor was a suggestion to use spent fuel from naval reactors and place that spent fuel, I'll come back to the diagram later, place that spent fuel next to a parapipide shape of uranium-238. Now that spent fuel would produce neutrons. The neutrons would propagate into the uranium-238 and breed plutonium. The plutonium would fission, produce neutrons, and breed more plutonium. And they suggest that the whole thing would, the fission processes or power production would proceed over maybe a 60-year period by breeding the plutonium and then moving into the area that is not yet bred. So that you put all a big parapipide here inside a large enclosure pressure vessel, and over a 60-year period, you are producing the power. And they call it traveling wave because basically the motion of the front of the breeding itself follows the wave equation, which is, as you could see here, a partial differential equation in the neutron flux that produces the power in the reactor. And a second derivative, partial derivative in time, tells us it is a wave. It has a solution as a constant and e to the omega t. So it's a function of time and a function of space, x. You'll find that the wave supposedly would propagate in the breeding material. And the whole idea started and was studied the perceived advantages that basically the uranium isotope that is fed in the new reactors does not have to be enriched, because naval reactors use highly enriched fuel, and they dispose of it after they burn enough of that uranium-235. The fission reaction in the new process burns through the nuclear waste. Actually, they use uranium-238, which makes the process safer. The process creates a large amount of energy from a small amount of uranium. And basically, because the breeding process is used, then you have an infinite supply of fuel, which is the vision of nuclear energy. Without that vision, we would not have nuclear energy. This is, they tried to use sodium as a pool design. And over time, the geometry deteriorated from the parapipide geometry into a cylindrical geometry, as you could see here. So they came back from the idea of a wave reactor, kept the idea of using spent fuel from naval propulsion, like nuclear submarines, because that is highly enriched and has lost its enrichment. So it's unsuitable for production of power in nuclear submarines. And they came back to the concept of a liquid metal fast breeder reactor. So the traveling wave reactor is now a liquid metal fast breeder reactor. And the company is named TerraPower LLC, based in the state of, in Seattle, the state of Washington. Here they show us conceptualization of a toroidal configuration. So That would be several of those modular reactors. So that's another thought with the heat exchangers on the top. So they are really modifying the idea, and maybe it will take shape in our future. The coolant in that case is a standard coolant like light water reactors, water, actually no, it has to be a molten salt reactor because molten liquid metal reactor, otherwise it cannot breed with fast spectrum. But in comparison with other reactor systems, the PWR, the BWR, you notice that the power density, as we introduced it as a criterion or a figure of merit to compare different reactors. In the PWR, it's 100 megawatt thermal per meter cube, or you can think about it as 100 watts per centimeter cube. Take a centimeter cube and put into it the power from a light bulb of 100 watts. The boiling water reactor is only a 50 watts bulb in a 1 centimeter cube. The CANDU that uses heavy water is much lower. And the gas-cooled fast reactor, we said that is allows us to get very high temperatures and allows breeding. It's the same as the PWR, but when you use the sodium, notice here how high you can go in the power density, 4 times or 3.5 times the one that you get from existing PWR. If you use a lead fast reactor, a lead bismuth to be more exact, that's about 70 megawatt thermal per cubic meter. And the very high temperature gas-cooled reactor would be very low. That's a reactor that is cooled by helium, moderated by graphite. So you could see here we have many different ideas. Each of them has some relative advantage in our future. So that was the traveling wave reactor. The French came up with the idea of underground water power plants. The idea obviously is taking from building nuclear submarines. That idea is that if an accident happens in the reactor underwater, water is a very good shield against radiation. And they are studying it, and they came up with some designs. They call them the small modular reactors. The idea is being studied in Japan, Russia, and also other countries. But France, really, naval construction firm, it's called DCNS, agreed with Arriva, which is, and Électricité de France, which is their electrical utility. Notice that France uses 70% of the electricity in France is produced by nuclear power. So it might see the light of the day. The length would be cylindrical shape, 100 meter in length, length of a Olympic swimming pool, and it would produce from 50 to 250 megawatt electric. So that is the underwrite for a reactor. An American company has taken the concept also very seriously. That is the combustion engineering company, and they're talking about a modular integral compact underground reactor. So instead of building a single unit that would be, say, 1,000 megawatt electric, a utility can split the construction over 4 maybe small units to 150 megawatt each. Again, the new technology or the innovation comes in from adopting technology from naval reactors, where you would have the steam generator and the core of the reactor in the same enclosure. They're designing it to be underground, so that would be a single unit, and then a utility that needs to produce power would add 1 unit after the other as the need arises. So here you have 125 megawatt electric unit, another one, 125 megawatt electric, another one here and another one here, that can be added sequentially, starting with a small unit that would cost us about $500 million. Utilities can raise that money very easily. They're underground, they are safe, they're an integral type, there is no risk from earthquakes, and they can be added really incrementally as the need arises. So this is the Babcock and Wilcox company, and you know that Babcock and Wilcox has been building nuclear submarines, so they are taking their part of the technology. Again, it's an integral type of a reactor. The reactor core here is at the bottom and the steam generator at the top, all of them enclosed within a single steel vessel, so there is no piping that can break in an earthquake and release the coolant or lose the and steam and radioactivity to the environment. And if it is underground, well, then it is not going to release any radioactivity in the case of an accident. They list quite a few advantages. They use, of course, a PWR concept, so that's established technology already. They can manufacture that reactor in a shop and then ship it to the location where it's used, and then after it is used, it's used back for recycling. It offers, in that case, because it will use low enrichment, about a 4.5 years replacement core design. I think there is no need whatsoever to go to the low, small enrichment. It's some kind of an arbitrary choice taken by Admiral Rickover when he started the nuclear navy in general. So for utilities, the small reactor has several advantages. Small reactors are expected to cost about $5,000 per kilowatt electric installed capacity. So that would be, if you take 125 megawatt electric plant, it would be 125 multiplied into 1,000 kilowatt electric by $5,000 per kilowatt electric. So in that case, each unit would cost the utility about $600 million instead of going directly into, say, $4 or $5 billion for a 1,000 megawatt unit. Large reactors cost maybe from $5 billion, depending on the manufacturer and the conditions of the purchase, to $10 billion for reactors that would range from 1,100 to 1,700 megawatt. So the future really is for a small unit to be developed and implemented, at least in the United States and maybe also the rest of the world. All right, so we covered as many concepts for reactor as we can, and we always have been mentioning the idea of enrichment. Why is it that we need to increase the amount of uranium-235 proportion in the fuel that we use? So you'll find that a whole new technology of dealing with the isotopes, it's called isotopic tailoring. Different isotopes from different elements have different properties. We know, for instance, that uranium-235, being an odd mass number isotope, 235 is odd, can fission readily more than the uranium-238, which is a more abundant isotope. So you find that there is a need to separate the uranium-235 from the more abundant uranium-238, in fact, increasing the proportion. In nature, uranium-235 is only 0.72% uranium-235 in uranium, and we can increase that level to the 90% for naval propulsion, or for, well, that's for weapons too. 20% is the limit for research reactors according to the Non-Proliferation Treaty and the IAEA. If we use the CANDU type of a reactor in Canada, or the heavy water reactors, we are doing enrichment, but not enrichment by the heavy elements. We are doing enrichment of the light element, in that case, deuterium in hydrogen. On Earth, deuterium ratio to hydrogen, the D/H ratio, is a 650 parts per billion. For the future, if you want to implement fusion energy, we'd like to separate the isotope of lithium-6 from lithium. Interesting enough here, lithium is going to compete for fusion energy in the future with the lithium that's used for electrical car batteries lithium-ion batteries, batteries for car. Boron-10 is another isotope that is separated from boron. Boron-10 has a very strong absorption probability or cross-section for neutrons. So in that case, we use it in the control rods of nuclear reactors or to shield against nuclear radiation. And it is also used in nuclear medicine because it absorbs neutrons. If you inject a soft tumor like a brain tumor with boron-10, then irradiate it with neutrons, that would help destroy that will help destroy the tumor, the soft tumor in the brain. You'll find that industrial countries have large commercial plants. Japan, South Africa, Brazil, Argentina, Pakistan, the Democratic People's Republic of Korea, and Iran. 4 major suppliers of services are in the United States, Department of Energy, Eurodif in France, Urenco, that is a British, Dutch, and German group, and Technap Export also in Russia. So it's a very highly sophisticated process, and that is a whole technology by itself. Let's look at some of the applications of isotopic tailoring or enrichment, and basically dealing with the different isotopes. The stable isotopes are produced by isotopic separation, as we'll learn in a moment, are used worldwide in both medical and industrial applications. For instance, in medical applications, you either do diagnostics and imaging, or you do therapy, depending on the radiation that you get from the isotope. The 2 most important techniques in nuclear medicine imaging are what's called the gamma imaging. So in that case, you use isotopes that are producing gamma radiation. So gamma imaging uses some stable precursors for gallium-67, zinc-68, zinc-67, indium-111, iodine-123, and xenon-124. There are about 20,000 gamma cameras in use all over the world. The radioisotopes are very extensively used in medicine. There's another process that's called positron emission tomography. In that case, isotopes that produce positrons, the antimatter of the electron. And when the positron is emitted, it interacts with an electron and it emits 2 gamma photons. That's called the annihilation process, a positron and an electron turning into energy or electromagnetic radiation. That process can monitor processes in biology, say what's happening in the use of sugar, say in the brain. And there are 200 positron emission tomography center in the world. We have one, I think, in Peoria here, and it comes and visits us in a truck when its use is needed for patients in Champaign-Urbana. Radiation therapy is, so if you do not do just plain imaging, you do therapy. And unfortunately for men, a large proportion of men end up having basically a prostate cancer. And to treat the prostate cancers, a process called brachytherapy is used. So in that case, you use an isotope iridium-191, and it decays into iridium-192. It's radioactive. So these are little pieces of metal that are inserted into a prostate that has of a man. 10% of men end up getting prostate cancer. In fact, we are having 300,000 new cases of prostate cancer are diagnosed every year in the United States and the European Union alone. So the iodine-125 also decaying from xenon-124 are used. And in brachytherapy, you insert little beads of those radioactive isotopes into the prostate that is afflicted by cancer, and the radiation kills the cancer in that case. It's also used in palliative care. It's called pain relief for people who are terminally ill. Basically, if they have secondary metastasis, say from the livers and to reduce the pain over the rest of their lives. For instance, breast cancer spreading to the rest of the body, or prostate cancer, lung cancer. These are all ideas under development to reduce the pain of people who are afflicted by metastasis. Metastasis is the spread of cancers, and it becomes non-curable in that case. So this is the medical applications of the different radioactive isotopes. It's a whole huge field for those interested in developing new technologies and new ideas for curing disease. Industrial isotopes in industry, in mechanical and chemical engineering are also used. For instance, if you use the depleted zinc 64, you can use it in the nuclear industry. When you add natural zinc to nuclear cooling water, that inhibits the corrosion. So that's important in chemical engineering. So natural zinc contains 48% zinc 64, and as a coolant water in nuclear power plants is exposed to continual neutral bombardment, it becomes a radioactive isotope zinc 65. Now this is a very strong radiation emitter. So if you remove that zinc 64 from the zinc and use it as an alloying element in the steel used where water goes into the nuclear reactor, then in that case you can reduce the radiation doses of personnel in a nuclear power plant. The United States Electric Power Research Institute, in fact, recommends the use of depleted zinc. The added zinc reduces the amount of radioactive cobalt-60 formed because of the irradiation of natural cobalt in the construction materials of the reactor. And cobalt-60, as we have seen in the chapter on food irradiation, becomes a very major emitter of gamma rays. Very strong gamma photons are emitter. And it's also a major cause of the radiation that builds up from the crud in some nooks and crannies of the cooling systems in nuclear power plants, and contributes to the radiation doses of personnel. Another application that is being under research is how to get rid of the actinides like the americium and the plutonium, maybe even that is produced in the nuclear power industry. So for instance, molybdenum 95, the isotope 95 of molybdenum is used in an experimental process of transmuting the long-lived radioisotope present in the nuclear fuel. Americium in the form of americium oxide is embedded in a matrix of molybdenum metal processed to cermet pellets and irradiated in a nuclear reactor. Non-destructive testing sources also would produce neutrons for us or gamma rays for all kinds of non-destructive testing methods. And the semiconductor industry has found some applications in the miniaturization of chips that would require ultra-pure silicon, germanium, and gallium materials to build a new generation of semiconductors. So these are really a large range of a new industry coming out that uses the properties of the different isotopes of the material. So we deplete some isotope or if we increase some isotope and we get different properties in the materials that we use. This is the field covers both medical application as well as industrial applications. Let's look at some of the typical applications in the nuclear industry using a chemical exchange to treat the isotopes. And we did mention one of them is that if you want to use natural uranium that has 0.72% uranium-235, you need to moderate the energy of the neutrons, not using the ordinary water H2O, but you want to replace that hydrogen atom by the deuterium atom. So it would become D2O or heavy water, and or HDO because you don't, sometimes you cannot replace all the two molecules. It's a combination of HDO and D2O. Now, why do we call it heavy water? It's very obvious. It is not hydrogen, and deuterium is heavier than hydrogen. But not only that, the physical properties themselves are different. The boiling point of heavy water is higher than the boiling point of water. So you can separate them just by boiling one preferentially to the other. Another reason it's called heavy water is that the density of ordinary water is standard, 1 gram per centimeter cube, but you find that the heavy water has a density that's 1.1 gram per centimeter cube. So if you choose to use natural uranium and not have to seek the enrichment services of industrialized nations, if you are a nation that wants to use its own resources of natural uranium without sending it for somebody to increase the enrichment to the 3 to 5% for light water reactors, you have to enrich your water, coolant water, into the heavy isotope. And it's easier to enrich the light isotopes like deuterium and lithium, boron, than it is to enrich the heavy isotopes like uranium and plutonium and so on. So in Canada, because Canada opted to develop its resources in natural uranium and not depend on, say, the United States or the Europeans or Japan or the Russians for enrichment services, they basically developed their own supply of heavy water supply. So this is the Darlington 935 megawatt heavy water reactors with the reactor complex at Ontario, Canada, providing Canada, the east part of Canada with electricity. But they're very smart. They also export that electricity, in addition to electricity produced from the Niagara Falls, to the east coast of the United States, like cities like New York, for instance, and making big money out of it. So that is an industrial process. Heavy water is very interesting in that it is definitely heavy. And if you get a beaker and place it in your freezer, you'll find that ice forms, and ice in light water has a lower density than the water, so it floats. But not so in heavy water. Look at this. This is a beaker of heavy water, and when you form ice in heavy water, it is heavier, so it sinks to the bottom. So this is an experiment to differentiate between light water and heavy water. One process is to use electrolysis, and that has been used. If you go back to the German program in the Second World War, the Germans basically tried to build a reactor using, actually it's a critical assembly. The reactor never became critical, but they tried to get heavy water from Norway. And in that case, the heavy water, because Norway has large supplies of electricity, the heavy water was produced by the electrolysis process. So how do you do that? If you run a DC current, direct current in ordinary water, you'll find that the ordinary water dissociates into hydrogen and oxygen easier or more readily than it is than the heavy water. So if you produce a cascading process where you start with a cell where you run DC current, you will preferentially evaporate the light water. So you get a concentration in heavy water. And then you repeat the process over and over and over and over. And as you do this, you end up with a concentration of heavy water to the level of 90% heavy water in water. And that was done in Norway during the Second World War. Norway is famous for its fjords and hydroelectric power supplies. You could see here water getting into a hydroelectric power plant run by the utility in Norway, Norsk Hydro. And the basement of that utility during the Second World War was producing heavy water in a series of cells. Here you find that 18 cells. You run a DC current. It's very cheap from the power plant, and repeat the process over and over and over and end up with 90% heavy water in the end there in those electrolysis cells. If you read the history of the Second World War, that plant became the target of bombing raids by the Allies against Norway to destroy their source of heavy water that they needed for the research in nuclear energy. And remember that fission was discovered in Germany by the two chemists, Otto Hahn and Franz Streichmann. Commando raids and bombing raids and even sinking a ship that was carrying drums of heavy water into Germany were conducted. So that was lots of intrigue during the Second World War, and Germany failed in producing any kind of a nuclear device in general. There is another way of producing heavy water using, again, a physical property of the heavy water is that light water has a lower boiling point than heavy water. And in fact, in nature, that happens in the Great Salt Lake in the United States. It happens also in the Middle East, in the Dead Sea. So with evaporation, preferentially evaporating light water, we end up with a lot higher level of heavy water in those two wonderful lakes. So this idea is implemented into an industrial process using fractional distillation. The same way as different products in petroleum, like gasoline and kerosene, have different boiling points. You use basically a tower, a distillation tower here, typical of refineries in general to produce different petroleum products. And you cascade the liquid from the top to the bottom. And as you cascade it on shelves here, those shelves would have different temperature levels. You can separate different parts of the distillate in petroleum. Now, this one is used with heavy water, and that was a plant at Savannah River here in the United States, providing heavy water for some plutonium producing reactors that they have been decommissioned at the Savannah River Laboratory here in the United States. So distillation towers can be 130 feet in height. So, and they use basically fractional temperatures. So here it's how the production process proceeds. You start from one side with heated water, and you add to it basically a chemical agent, a hydrogen sulfide. I'll show you the reactions in a moment. And you feed the water from one side, you heat it, and then you let it trickle from the top of the reactor on shelves. And in the end, you end up with enriched heavy water from the other side with the evaporated light water being recycled. At some point, you add hydrogen sulfide to the reaction. So what happens in that reaction? It's an equilibrium reaction that I'll show you in a moment. This is an Ontario, Canada heavy water production plant. And at some point in Iran, they had also constructed one of those plants for a reactor that we're trying to build at Arak. According to the agreement with the 5 nations in terms of the production of fissile fuel in Iran, that plant has been discontinued. That's a picture of it. But the reaction that happened basically by adding hydrogen sulfide is that you get steam. Well, water is heated steam. Water is steam, and you add to it hydrogen sulfide. Let's take a hydrogen sulfide where we have a hydrogen atom, a deuterium atom, another isotope of hydrogen. And this reaction, basically upon heating it, turns into hydrogen sulfide H2S. And then you find that that H2O now replaces one of its hydrogen atoms with the deuterium from the hydrogen sulfide. So you end up with HGO. And that reaction is reversible. That's a sign for reversibility. At a given temperature, this reaction has, in physical chemistry, an equilibrium constant. So the equilibrium constant K is the concentration, the square brackets denote concentration of the HGO multiplied into the concentration of the H2S in the product divided by the concentration of the water in the reactants and multiplied by the concentration of the HDS in the reactants. We can just modify the ratios here. You find that the concentration of HDO now into water and the concentration of HDS in H2S is a constant that depends on the temperature. At 25 degrees, that constant is 2.35. At 128 degrees Celsius, it's 184. So you take that to advantage by having different temperatures down the fractionation column, and you end up separating the two streams with the concentration of heavy water from the one that has less concentration in heavy water. So that is basically an enrichment of one of the light elements, deuterium and heavy water. In the future, we'd like to be able to produce lithium, separate lithium-6 from lithium in general for future fusion reactors, because lithium can absorb a neutron and turn into tritium, and then deuterium from seawater can be combined with tritium to produce a thermonuclear reaction. Now we know that it works in thermonuclear weapons, and humanity would like to adapt the process for future fusion reactor. So to separate that the lithium-6 from lithium in general, which has more lithium-7 than lithium-6, during the Cold War, a huge plant was built just for that purpose. It's shown here. It's called the Y12 plant at Oak Ridge, Tennessee. Oak Ridge, the green state, Tennessee is a green state, has good supplies of hydroelectric power and also has coal power plants producing large amounts of electricity. At Knoxville, Tennessee, you find our Alcoa company. Alcoa is the largest aluminum producer in the United States. Alcoa stands for Aluminum Company of America. In that case, to produce aluminum, a very strategic metal, you need electricity. And in that case, the United States government owns a utility. In that case, the Tennessee Valley Authority is a public utility owned by the United States government. And it basically provided the electricity for that Y12 plant to separate the lithium-6 from the lithium. There are three processes that they use: the COLEX, ELEX, and OREX processes. They're not documented in many different places other than here. And COLEX stands for the column exchange method. So in that case, you combine lithium with mercury. And in that case, you create what's called in chemistry an amalgam. It's an alloy of the two. So you get an alloy or an amalgam of lithium with mercury. Lithium-6 preferentially combines with the mercury than the lithium-7. So by getting an ion exchange process and columns exchange process, you can get a stream of the amalgam that is enriched in lithium-6. So this is a lithium solution tank used in that COLEX process. And once you have a stream now that has a more concentrated lithium-6, which is can be easily used to produce a tritium compared with lithium-7, you'll find that you take the amalgam and heat it. As you heat it, you remove the mercury, and you're left now with the lithium-6 that you can place in those flasks here to use in either producing tritium for thermonuclear weapons, or you use it for in the future for fusion reactors applications. The process of heating and burning the mercury released huge amounts of mercury to the environment around the plant, and that has been a cause of pollution that Tennessee still has to deal with. It was not done properly, and you can research that by reading the rest of the material right here. Boron isotope separation, as I suggested you, the boron-10 isotope is more suitable for use in control rods in nuclear reactors, and or you can use the boron-10 injected into a soft tissue tumor like in the brain, then irradiated with neutrons. The neutrons will split the boron-10 into two nuclei, like in that case, helium and lithium, and that would kill the cancer tumor in general. All right, so this is for the light elements. The light elements that we considered are boron, we considered lithium, and we considered deuterium. However, the isotopic tailoring industry also does it with fissile and heavy elements. In that case, we need to create a taxonomy here of the difference between what we call fissionable fuels and what we call fissile fuels. Fissile fuels are primarily the odd-numbered heavy isotopes of uranium, like uranium-233. See, it's an odd-numbered isotope, and uranium-235, odd-numbered isotope. Also, plutonium-239, odd-numbered, and plutonium-241, odd-numbered as well. And we can add to the list the artificially created isotope neptunium-237. All these isotopes are odd-numbered, and odd-numbered heavy isotopes are notorious for being very sensitive to the absorption of just an extra neutron in the nucleus. So if you add an extra neutron to the nucleus, these isotopes become unstable and very immediately fission. Hence, we call these isotopes, the odd-numbered isotopes, the fissile isotopes. That's a terminology or a taxonomy. Other isotopes can still fission, but they cannot fission with a zero energy neutron. Just adding a neutron to any of these isotopes would slip it into two parts. However, the other isotopes like uranium-232, uranium-234, 236, 238, and thorium-232, all of these are even numbered isotopes. Now, you can still fission those isotopes, but you need a highly energetic neutrons, not like these fissile isotopes where you need a zero energy neutron. It just has to do with the structure of the nuclear shells in the nuclei. Same as we have electronic shells in the atoms, we have nuclear shells in the nuclei. So in that case, that explains partly the process of breeding. For instance, thorium-232 would not fission by itself, and you cannot create a critical mass from thorium-232. So what do? You add a neutron to it, the neutron produces another isotope of thorium-233, then it emits a negative electron, then it emits another negative electron, turns into protoactinium-233, and the protoactinium decays into, uranium-233. So something that was fissionable becomes fissile. And in that case, we would be able to breed more uranium-233s and uranium-235 that we would have used to breed that uranium-233 from the thorium-232. And this is what we designate as the thorium nuclear fuel cycle. And the thorium in nature is, as we know, 4 times more abundant than uranium. And in fact, that's because it has a much longer half-life in radioactivity than uranium. You can also use uranium-238 through the breeding process and turn it into, from a fissionable isotope into a fissile isotope. You absorb a neutron in a nuclear reactor. In uranium-238, it turns into uranium-239. It emits a negative electron. It turns into neptunium-239. Neptunium-239 emits a negative electron, and becomes a fissile isotope now, plutonium-239. So we have really 2 breeding cycles here available to us in the heavy nuclei. One that's based on thorium-232, and one is based on uranium-238. So we can consider those fissionable nuclei as basically breeding nuclei. These are the equations that I just mentioned right now. A neutron in uranium-238 produces uranium-239, that one emits a negative electron. An antineutrino is always associated with a negative electron emission. That's neptunium-239. Neptunium-239 decays by emitting a negative electron. You get plutonium-239. If you add these three equations, you find that 239, 239 cancel, 239, 239 cancel, and you end up with a neutron added to uranium-238, producing plutonium-239, 2 electrons, 2 antineutrinos, and 3 gamma photons are also emitted. So in that case, the uranium-239, neptunium-239 take part in the equation, but do not appear as final product. In chemistry, we call this really catalyst. So that is a catalysis type of a reaction. We mentioned thorium as being more abundant in the Earth's crust, 4 times more abundant in the Earth's crust, but it doesn't have an odd numbered isotope, so it cannot create a critical mass. However, we can use that thorium-232, use a neutron from this other reaction where uranium-235 is being fissioned. It turns into thorium-233. It decays through negative beta decay, produces protoactinium-233. Protoactinium decays, emitting an electron, and we end up with uranium-233. Oh, that's a fissile nucleus now. So in that case, we would have bred from something that is not fissile, something that is fissile. And the thorium-233 and protoactinium are the catalyst. It's a catalyzed type of an overall reaction. I'll ask you to balance that reaction as an assignment just to get acquainted with it. The production of uranium and then enriching it is part of a larger process we call the uranium fuel cycle. There are 3 different fuel cycles that are being adopted, but it all starts with the mining of uranium. And the United States is very rich in uranium, but there are other countries that are even richer, like Kazakhstan and Canada. And uranium also is produced in the gold mining process in South Africa. This is in the United States, a mountain in the mining area of New Mexico called Hayesrack Mountain. It's very rich in uranium, but the United States is not mining uranium anymore because it can import it on the world market from Canada and Kazakhstan and South Africa and other countries. Canada is importing quite a bit of uranium. It's very rich in uranium. The company there is called Cameco, and it has an underground mine. In that case, it's, I think, the MacArthur River mine. They have one of their mines is under a lake, and it starts Cigar Lake, it's called, mine. And the water from the lake started leaking into the mine, and it stopped operations. And people joked about it, saying that, oh, maybe Cameco should produce hydroelectric power in its mine. In any case, this is mining of uranium in Canada. The mines can be above ground mines. You could see here the overburden in one of the mines here in the United States in the area of New Mexico. This is another mine, another part of the world in Namibia. So this is above ground pit mining, as it's called. But there are also underground mines. So you could see that mine here in the area of Grants in New Mexico. If you have a mine that is underground, the decay chain of uranium-235, as we have looked at it earlier, produces a radon gas, and radon has a low boiling point, so it is emitted at room temperature as a gas. And then the miners in that case can inhale that radon-222, and the radon-22 ends up decaying itself into polonium-210, which is extremely chemically and radioactively toxic, and lead-210. So in mining underground, you notice that engineers have to really ventilate the mine. So you could see here that's a ventilation shaft in one of those underground mines. This process is not being conducted in the United States now. Again, as I said, uranium is very cheap. something like $20 per pound of U3O8, the oxide of uranium. But at some point it was being conducted. Today, people who are not well versed in knowledge and science, they go to those mines and sit there supposedly to help with their arthritis. They call it rheumatism. And in that case, they inhale that radon, and it turns into their lungs into polonium-210 and lead-210. And it is a very bad practice, but that's how mine shafts in the United States are used today. Those who smoke cigarettes, as we know, also would end up with particulate matter of that polonium-210 and lead-210, which produces radioactive toxicity from smoking cigarettes, in addition to the chemical toxicity from the benzoapyrene, which is a cancer-causing element in the smoke of cigarettes. After uranium is mined out west, you could see that the mine areas are reclaimed. This is an older underground canyon, a Poison Canyon uranium mine site. You could see you cannot differentiate it from the surrounding deserts. At some point, people made fortunes by getting mules, getting a geologist hammer, and going out west on their mule with a Geiger counter mule tube. We have seen those in a previous chapter, and prospect for uranium. Some of them probably became very rich by discovering mines. And if you go out and travel west and visit some of the national park where they have basically trees that have been fossilized, the fossilization process replaced the cellulose in the wood by uranium. So that gentleman there is basically looking at a petrified tree logs exposed by flash flooding in the desert of probably New Mexico, Ambrosia Lake, New Mexico in general. So if there is a new need for uranium in the future, get yourself this is what some people would be doing, prospecting for uranium. Once you find uranium, it comes out mixed with with earth and other minerals. So you have to separate it and refine it and convert it. So it's a whole industrial process that is shown maybe in that diagram. So you start by mining uranium in the form of U3O8, which is uranium oxide. And the ground usually is only 0.3%. Has a U3% in the United States. Like in other countries, like in Europe, there are different forms, like pitch blende is another ore of uranium discovered in Czechoslovakia. In South Africa, they'll get uranium in the ore when they mine gold. Uranium and gold have the same density that then when they concentrate it through geological kind of phenomena, they occur together. Okay, let's think about the United States. So in that case, you take that ore and you crush it. Then you put it through a milling and refining process. We've shown one of the mills in Canada in an earlier picture. And in that case, you separate that U3O8. That oxide has a yellow color. So in that case, it's called the yellow cake. And so that is from mining to milling and refining. The yellow cake is taken now in 55-gallon drums, standard size for drums for petroleum uses, to a conversion process. And many, many companies are involved in that process. In the United States, the Allied company. In Canada, it's Cameco. In the UK, it's Kogima. Actually, in the UK, it's a British Nuclear Fuels Limited. Kogima is probably France. And you convert that U3O8 into a fluoride of uranium, uranium fluoride. And that is a process called fluorination. You add fluorine. Why fluorine? Fluorine in nature has a single isotope. So if you want to separate the isotopes of uranium-235, 234, and 238, you want a chemical compound that doesn't have many isotopes itself. You notice that fluorine has a single isotope, fluorine 18 only. So in that case, you end up with molecules that contain different uranium isotopes, but the same fluorine isotope. You store that uranium hexafluoride in steel cylinders, and you take it to an enrichment plant, and then we'll look at different processes for enrichment as we proceed further. In the enrichment plant, you end up with two streams of enrichment. The 3 to 5% enrichment in uranium-235 is really what is used in the fuel fabrication in companies like General Electric, Westinghouse, Toshiba, as nuclear power plant fuel. That 3 to 5% is totally arbitrary. It was decided by Admiral Hyman Rickover when he developed the nuclear navy of the United States, and he didn't want uranium in high enrichments to be floating around. So he gave up a number. Oh, we cannot have uranium floating around at higher than 3 to 5% from nuclear power plants. And that results in a large core of the reactor and not necessarily an optimal design. However, what's important there is that those enrichment plants can also produce 93% enriched uranium, both for the production of weapons as well as naval reactors. So they find that naval propulsion uses highly enriched fuel. If you produce highly enriched fuel for naval propulsion or from the 3 to 5% for power plants applications, you end up with what is called depleted uranium. And now in that case, it has only down from the 0.72% uranium-235 in natural uranium is down to 0.2% to 0.45% in natural uranium. You store it because the content in uranium-238 has a future use in breeding. If you absorb it neutrons and develop liquid metal fast breeder reactors, when the price of uranium becomes higher by depleting our supplies to a certain extent, then we can use that heavy uranium-238, the fissionable or the breedable material in breeding plutonium and getting extra supplies of energy from fission. However, uranium-238 has also found some very interesting use. Uranium has the same density as gold, 18.9 grams per centimeter cube. And you know that gold has a very high density, much higher than lead. Lead is only 10 grams per centimeter cube. Actually, it's the same as silver. So silver and lead have the same density, and they can be basically cheated against each other. Don't buy silver that is in fact lead on the market, and don't buy actually also we have tungsten that have very close 20 gram per cc, very close to the density of gold. So gold ingots get cheated by tungsten, which is cheaper than gold, obviously. In any case, the high density of gold has turned it into a weapon in the sense that a high density projectile, 18.9 gram per cc, can penetrate very easily steel, which has only a density of 8.9 8 gram per centimeter cube. So if you use steel, say a knife, you can cut through wood. And in that case, your uranium, 18.9 gram per cc, can cut through steel. That's only 8 gram per cc. So it has been used as an anti-tank projectile. It doesn't need to be explosive. It will just penetrate the walls of a tank or a fortification and then explode with particles to all by itself through its kinetic energy into a particle to a very large surface area. And that basically starts an explosion or a fire inside the walls of a tank. So that was meant as a weapon against the Warsaw Pact nations by NATO, the NATO organization for a potential war in Europe. But the hapless Iraqis ended up being the target of that weapon with great devastation to their troops and fortifications and underground bunkers and so on. Because it can penetrate steel, it also can resist steel. So you find that uranium projectiles are used also in the walls of tanks and personnel carriers. So uranium, basically 238, has found its use both as enriched uranium in power plants and as well as depleted uranium in weapons for the military, both offensive as projectiles and defensive as shields to shield personnel in tanks and personnel carriers. All right, now you burn that 3 to 5% fuel in nuclear power plants, you end up with fissioning most of that 3 to 5%. When it comes down to 1%, there is still some plutonium produced there. So either that you take it as spent fuel and store it for permanent storage underground, the same way that we mine the uranium from the ground here, or we return it back to the ground, or we keep it for a while until the radioactivity decreases, recycle it, and use that plutonium that is produced in it after burning out the fuel in the reactor. So after burning the fuel in the reactor, the uranium now is from 3 to 5% uranium-235 is down to less than 1% uranium-235, is stored right now in spent fuel tanks awaiting the recycle. That is in the United States, but in other countries of the world, the recycling is being conducted. The plutonium is extracted and then is experimentally being fed now as what's called the mixed oxide. That's the oxide of uranium mixed with the oxide of plutonium, UO2 plus plutonium-238. The thorium cycle, unfortunately, has not been started in many countries, even though gas-cooled reactors have been, as I've shown you in the chapter on gas-cooled reactors, there have been several pilot plants using thorium. It will be used in the future for breeding, and if we are going to develop a transportation system using hydrogen and fuel cells, we need to use a thorium cycle. The process of refining and turning the uranium into a useful form for power plants starts, as we suggested, with first getting the ore, crushing the ore using flotation process like in the mining process, and ending up with what's called the yellow cake. I'll show you a picture of it soon. That is 65 to 85% U3O8, the oxide of uranium. You dissolve it in nitric acid. It's a very, very elaborate chemical process. In that case, you get a uranyl nitrate solution, UO2NO3, nitric acid, creating that compound. But that solution is impure. It contains elements like vanadium, for instance, mixed with the uranium that can absorb the neutrons in a nuclear reactor and affect the chain reaction. So you put it through a solvent extraction process, simply circulate it into a solvent. Could be as simple as kerosene. And then in that case, you get now a purified. So you take the uranyl nitrate that's impure and you purify it into a uranyl nitrate solution. Then you precipitate it with ammonium hydroxide and you end up with ammonium diuranate, ADU, which is ammonia here and U2O7. In that case, you have purified the ammonium diuranate. Then you calcine it, meaning that you put it through an induction kind of a furnace mixed with calcium, or some people use magnesium. The same reaction will happen. And you add to it hydrogen. This is a precipitation process. And you turn your ammonium diuranate mixed with the calcium now, or the magnesium, into just plain UO2, which is uranium dioxide. That is what's called the brown oxide. If you want to get the uranium metal out of it, you treat it with hydrofluoric acid, hydrofluorination, and that hydrofluorination turns your UO2 into UF4, uranium tetrafluoride. You fluorinate it a second step, and you end up with uranium hexafluoride. Now, this is at room temperature, a solid a crystal. And when you heat it, it's stored in large steel tanks. And when you heat it, you can use it as a gas in the enrichment plant that primarily uses uranium hexafluoride. This is not pie in the sky. This is here a uranium mill picture at Key Lake in northern Saskatchewan in Canada. You can see the hue of yellow here, which would be that U3O8 or the yellow cake. This is a refinery now, a huge industrial process, as you could see, at Blind River in Ontario, Canada. And the uranium that's produced in Canada is used in Canada in their heavy water reactors design, a very successful design, as we have seen earlier, or for exports to other parts of the world as natural uranium. They are not involved in the enrichment process other than producing heavy water. This is an actual picture of that yellow cake that we have been talking about. That's U3O8. If we use uranyl nitrate, that's a liquid. That's a flask containing that uranyl nitrate. And then you produce in the diagram the ammonium diuranate. That is that brownish powder here. And then you have the uranium dioxide shown here right there. We said that the U3O8 is named the yellow cake because it's yellow. And here it is in 55-gallon drums in the manufacturing process in general. If you want to produce uranium metal from your uranium dioxide, as I said, you mix it with magnesium or with calcium. You place it through induction surfaces. You end up with a slag of the the oxygen mixing with the magnesium or with the calcium, and you end up with an ingot of metal. And these are ingots of uranium metal, as you could see here. Each one of those would be the weight of a small Volkswagen. Each one is 1,100 pounds each. So you really cannot carry that whatsoever. It will break your back. There is use for the metal itself. It's also a good way of storing it. The uranium hexafluoride is stored in large steel tanks, stainless steel tanks for corrosion. And inside the tank, it turns into a crystal. When you take it to the enrichment plant, as we'll see next time, maybe, you'll find that you evaporate it and you use the gas in the enrichment process. In that case, you separate uranium-235 from the uranium-238. This is a little glass vial showing us really those uranium hexafluoride crystals before they are, of course, heated and fed into the enrichment plant. In the end, you end up in the enrichment plant with enriched uranium or enriched, in that case, actually, these are two pucks, as I have called. The name of pucks comes from simply the pucks used in the game. And notice that the two gentlemen holding them have rubber gloves, vinyl rubber gloves, not to protect themselves as much as it is to keep the oils or fat from their hands affecting the uranium. Now, why are they flat in the form of plugs like in the hockey game? Because you'll learn later that if they were in the form of a sphere, the surface to volume ratio of a sphere as a geometrical figure is the least of all the geometrical figures. In that case, the leakage of neutron from the surface is minimum. And that's why when we create a critical mass, we are going to use the sphere as a critical shape. When you flatten the puck of uranium in this shape here or there, that's uranium-235, you'll find that the surface to volume ratio is high. So the neutrons that are produced may be from spontaneous fission or from neutrons produced by cosmic radiation in the Earth's atmosphere. Neutrons are produced when cosmic radiation hits the nitrogen in the atmosphere. Then the leakage from the surface would be high enough so that you don't get a critical mass. So the critical mass can occur not just in those pucks of uranium, but if you have, say, a bucket that contains a uranium chemical solution. So we have to be very careful, and accidents have happened, in fact, in those recycling plants, like people being in a hurry to go home over the weekend, being sloppy in their work. And if you reach accidentally critical mass, that can cause accidents and, in fact, the deaths of people in general. We look today very quickly now in the remaining time for the different fuel cycle that we adopt in the operation of nuclear power plants. The existing cycle that we use today in the United States is what's called the once-through fuel cycle. So what do? You mine the uranium U3O8 from the ground, you turn it into uranium hexafluoride, you enrich it to the 3 to 5% for light water reactor use. And in the process, after you burn as much uranium-235 from 3 to 5% down to less than 1%, you take the spent fuel and you store it and end of the cycle right there. So it's a very wasteful cycle, because when you dispose of that uranium here in the fuel, you'll find that you are disposing of the fuel because it has been affected by radiation damage, and there still is that 1% of uranium-235 in it. Moreover, the uranium-238 has interacted with the neutrons and produced for you another fissile fuel, which is plutonium-239, and you try to simply dispose of it in the ground. Well, you can continue doing this as long as the price of uranium is cheap and uranium-235 is abundant. But sooner or later, within 50 years, you'll find that the price will go up because that cheap uranium-235 is going to be depleted. So in that case, you start thinking about the promise and the vision of nuclear energy in terms of breeding, producing more fuel than what we consume. So in that case, we talk about a different cycle that the Europeans and the Russians and the are using, and that's a thermal reactor cycle. So you take the spent fuel there and you take it to basically a reprocessing plant shown here, and you simply reprocess the fuel and put it back into a nuclear reactor. So in that case, you end up with some waste. The waste would contain only the fission products from the reprocessing plant, not the whole spent fuel rods from the reactor in the once-through fuel cycle. So these are the two cycles. One, a wasteful cycle used in the United States and some countries. The more advanced thermal reactor recycle used in Europe and Japan and Russia. In the future, as we end up within, say, 50 years, when we end up using the cheap supplies of uranium-235, if we use uranium, we have no choice but going to what's called the fast reactor cycle. In that case, you recycle the fuel, extract uranium in it, use the enrichment process, but make sure that you breed plutonium-239 as a fissile fuel. And in the process of breeding, we can produce more nuclei than we are burning. And in that case, it becomes an infinite energy supply if it is designed appropriately as a fast nuclear liquid metal fast breeder. There is another alternative, is of course to use the thorium cycle, and in that case we use thermal reactors, not fast reactors. Either way, before we deplete our uranium-235, we can end up with two unlimited fuel supplies for energy. An interesting fact, or that is not known to very people, is what happens with plutonium-239. If you don't use the plutonium-239 as a fuel, Let's look at what happened to it. A neutron is absorbed in uranium-238. It produces uranium-239. It turns into neptunium-239 by emitting a negative electron. Notice the balance here, 92 is equal to 93 minus 1. Then the neptunium-239 becomes plutonium-239. Well, if you do not use a plutonium-239 and burn it in a nuclear reactor, you dispose of it into the ground, it emits an alpha particle like uranium-235 and uranium-238. And look at the balance here. 94 emits an alpha particle, so its atomic number, 94 becomes 92. Oh, that's uranium. And what isotope of uranium? 239 minus 4 is 235. So if you don't use a plutonium that is produced in existing nuclear power plants, that plutonium, if we dispose of it, like in the wasteful once-through fuel cycle adopted in the United States here, it ends up back again into uranium-235. So nature is very interesting here. It is recycling itself. So a neutron, if you cancel the catalysts in that case on both sides of the equations, the chain equations, a neutron is added to uranium-238, and you extract some energy from it, produce an alpha particle, 2 negative electrons, 2 antineutrinos, and in the end, oh, you end up back to what you began with to produce those neutrons, which is uranium-238. That is an interesting part of nature taking care of itself. I'll stop